Hello, this is Lazarus at telecomTech, where telecom and networking technologies are simply explained. Today, we'll be simply explaining Label Distribution Protocol for MPLS. This video series takes a look at MPLS from first principles. We start from scratch and build up to more complex and detailed deployment scenarios. So whether you're new to MPLS or you just want to brush up on your understanding of the technology, this series is helpful for you. You can be notified of every new video that's published by subscribing and enabling notifications. And if you find this video useful, please do click that thumbs up button. In previous videos, we introduced MPLS as a technology that is used to efficiently direct data between nodes. And we examined a simplistic traversal of a packet across an MPLS infrastructure. In this video, we'll be taking a more detailed look at how MPLS routers exchange information about labels and how that information is used to populate various internal constructs in an MPLS router that make MPLS possible. First of all, when you have an MPLS core network such as this one here, you must have an underlying routing protocol that allows all of these devices to communicate with each other. So typically, you'll have something like OSPF or ISIS running so that these nodes here are able to find each other and communicate with each other. Now, mind you, the purpose of this underlying routing is not to get to the customer networks. It's only for the purpose of allowing these routers to find each other and to create the underlay network that will allow MPLS to operate. Now, this is kind of counterintuitive because you will typically want to use MPLS and label switching instead of routing. So why do we need routing? Remember, MPLS label switching is responsible for transmitting customer traffic. This routing underlay here that we're talking about is here to allow the control plane to function. Now, secondly, once you've established that underlay routing, when you have two MPLS routers and you enable MPLS on these interfaces here, LDP will automatically attempt to make an LDP adjacency. MPLS is enabled on a per interface basis, and we'll see that in practice when we configure MPLS routers in a future video. LDP adjacencies take place only between directly connected MPLS routers. Once an adjacency like this is established, labels begin to be exchanged. But where are these labels stored, and what is their significance? And how are they related to the IP prefixes of our customers that we want to relay over the infrastructure? To answer this, let's first take a look at the constructs used by normal IP routing that we all have come to know and love. When normal routing takes place, we have various entities within the router that enable it. We have the routing protocol, such as EIGRP, OSPF, BGP, or ISIS, for example. These protocols will run their algorithms and will discover the best paths within this infrastructure. Those best paths will be placed within the routing information base, or the RIB. Now, this is just another name for the routing table. Using various rules, including parameters such as administrative distance and routing protocol metrics, the RIB is populated. Now, from the routing table, another construct is populated, which is called the forwarding information base, or the FIB. It's essentially a subset of the router's RIB that is typically implemented in hardware for efficient forwarding and contains only the best routes selected for packet forwarding. Now, when packets arrive at this router here, it's the FIB that's used to determine the next hop to send the packet along its way. Now, when MPLS is enabled and LDP begins to exchange labels, we have some new constructs that are created within each LDP router. The LDP protocol is used to locally generate a label for each prefix that is found within the RIB. This creates the label information base, or the LIB, within which the prefixes in the RIB are assigned labels. The labels that are generated are only locally significant. This means that their actual values have meaning only for this particular router. The information in the lib is then used to create the label forwarding information base, or the LFIB. Now this is the counterpart to the FIB for routing. Essentially, when a packet arrives at an MPLS router, it is the LFIB that is examined to determine the next hop and send the packet along its way. Now the LFIB is often employed in hardware that is specifically designed for enabling ultra-efficient label switching. Now, since labels are locally significant, MPLS routers must know what label is being used for a particular prefix by its neighbors. That way, when it forwards it to the next router in the path, it will replace its own locally significant label value with the value that the neighboring router says it uses for that particular prefix. So for a destination network of 192.168.12.0/24, which exists on this customer network here, this PE router via LDP assigns a local label of 27. And this assignment is recorded in the LFIB. But this P router here has assigned a locally significant label of 29 for this same prefix. And through LDP, the P router informs the PE router of this information. So from the point of view of this PE router here, the local label is 27 and the remote label of the next hop node is 29. Now looking at the LFIB of this router here using this command on a Cisco router, we see the local label as 27 and the outgoing label as 29. So when this router sends a packet for the prefix 192.168.12.0/24 to this router, it will swap its own label of 27 with the label of the P router, which is 29, before it sends it out. And in the LFIB, you can also see that we have the outgoing interface as well as the IP address of the next hop. So the label switching process at this router has all the information it needs to send the packet to the next node in the path. Now the process continues when the packet gets to P1. You can see that the local label is 29 and the remote label of the next hop router is 31. So it swaps the labels and forwards the packet with the new label to P2, which is the next hop router. Now what we see in the LFIB for P2 is interesting. We see the local label here is 31, but for the outgoing label column, which is essentially the advertised label from the network PE router here, we see POP label. This simply means that before sending the packet, it will simply remove the label and send it to the PE router with no label at all. This is called penultimate label popping. The word penultimate simply means second to last. By definition, the last P router you encounter in the path is always the second to last router that's encountered along that path. So this penultimate router will pop the label or remove it before sending it to the PE router, which is the ultimate or the final router in the path. Now we look at the LFIB of this PE router here and we'll see that we don't find the 192.168.12.0/24 network in the LFIB at all. Why? Because PE routers don't have a label assigned to the networks of the customers to which they are directly connected. This is because PE routers and CE routers will have a routing protocol running between them. So routing here takes place using conventional routing protocols. And it is for this reason that the penultimate label popping takes place. So once the packet reaches the PE, it is simple routing that will direct it to the CE and to the final destination network. So hopefully going through this process, you can see how LDP works, how labels are exchanged, how the LFIB is populated, and how local and remote labels are used to allow MPLS to operate. Well, I hope you found this video useful, and if you have, please click that thumbs up button. If you have any questions or feedback, please feel free to leave a comment, and please subscribe to get updates of newly published videos. I'm Lazarus at telecomTech. I hope this video has been helpful for you, and I'd like to thank you for watching.